All right, so today my team and I are going to be talking about our project, the Trotton Trailer, and our project involvement with Charles Machine Works. So just a brief introduction about the team. I'm James Collingsworth.
I'm Connor Kay.
I'm Skylar Shepard.
Colton Leach.
Trey Minton.
So just a little bit about the client. So Charles Machine Works produces various types of equipment such as skid steers, directional drills, trenchers, and vacuum excavators. They were actually founded in 1902 and they're headquartered in Perry, Oklahoma. So the brand name that most of you guys are probably familiar with is Ditch Witch. Well, Ditch Witch is actually a trade name of Charles Machine Works. So for our project, our goal was to instill our core values throughout our design, such as dependability, innovation, and safety.
So our problem statement was our company wanted us to build a device that allows the FX30 trailer to be moved independently without the help of a vehicle. So a little bit about the trailer is they use it for directional cleanup. They use it in commercial and residential areas. And the main thing is they use it for potholing. And if anybody's potholed by hand, it's not any fun. So this device helps out a lot. And nowadays, when you pothole and you have to see the exposed bury line, when you're digging another line to go under it, you have to visually see it.
A little demonstration here of it. So upon meeting with Ditch Witch, they specified a few designs that a few parameters that our design must meet. Must be able to operate on hard surfaces such as concrete, asphalt, and gravel. It's not designed to work on mud or sand. The design should be self-propelled. What we mean by that is the system must be able to drive and steer itself without the use of a standard motorized vehicle. The system must be integrated onto the existing trailer. So for our design, we were given the FX30 vacuum trailer. So our design had to be integrated onto that trailer. The system should be simply engaged and disengaged. This was a big factor for Ditch Witch. They wanted our device to be convenient not only for them, but for their future customers too. Controls need to be operated by remote control. Also another factor of convenience. They didn't want to restrict the proximity of where they're able to use it. And for the top speed, the system should be able to reach between 1 to 1.25 miles per hour, which is essentially a slow walking pace.
So this is a diagram of the FX30 vacuum trailer that we used. You can see in the back over here is the storage tank. Then you have the water tank in front of it, hosing, and then the engine, diesel engine up front. With an 800-gallon storage tank in the rear, you could tell that the weight distribution across the trailer would be very uneven, and this caused a lot of problems during our design problem and challenges as well.
So a little bit about the trailer is, as you said before, we had the 800-gallon tank, but there's also another variation, which is the 500-gallon tank. That one loaded only weighs about 10,000 pounds, but the one we had, when it was loaded, it weighed 18,000 pounds. So the engine that comes equipped on this trailer is a Kubota engine. It produces 24.8 horsepower at 3,000 RPM. And the existing hydraulic system on the trailer was it produced 2,500 PSI with a flow rate of 2 gallons per minute. And from the picture, you can see we actually hooked up our own pressure gauge right behind the pump on the trailer, and we read out 2,400 PSI was what we had for the system.
So this is our project breakdown starting from last August. The group started by picking a project and then brainstorming. After meetings with Ditch Witch, we were able to further our design. And late last year, we completed our final design concept. Beginning this year, we started finding materials, and beginning February, we started fabrication, and then afterwards, we began testing our design.
So while we were in the early brainstorming phases of our design, we wanted to look at some relevant technology that was capable of moving our FX30 vacuum trailer, which led us to look at trailer tugs. So the Hall E trailer tug is capable of towing up to 50,000 pounds or 40,000 pounds with a max tongue weight of up to 15,000 pounds. But what we really liked about this most is the fact that it's able to be controlled via remote control for the drive and steer, which is essentially what we aim to do for our design. So initially we were designing for trailer tugs, but after meeting with Ditch Witch a few times, they actually specified that they in fact did not want a trailer tug. because they want our design to be integrated onto their existing trailer.
So we looked up some relevant patents also. This was a lift axle, which is what we based our 3 drop-down axles upon. The importance about this is when it's down, it just redistributes the weight of, or in our case, the trailer. And when it's lifted, you can move it easily down the road and it doesn't cause any problems.
So one of the things we had to accommodate for in our design were trailer regulations. Our design cannot exceed the width of the trailer of 102 inches or add to the length of over 40 feet. It also had to be safe to operate around people and while on the road.
So this is we ended up putting together a free body diagram to figure out where the weight distribution was of the trailer so that way we could design accordingly. And how we ended up doing this is we took the trailer to a local truck scale here in town and we found the weight of the trailer at a few key points, including at the tongue and at both of the wheels, both of the tires, as well as the full trailer weight. And what we did is we designed so we were able to find the center of gravity of the trailer, approximate the center of gravity of the trailer, so that way we could do the free body diagram to figure out where our weights were going to be and how much weight we needed to, how much force we needed to generate. And we ended up designing for the worst possible conditions we could foresee. And at 18,000 pounds, the axles of the trailer could only handle a slope of about 8 degrees before the axle of the trailer itself reaches its rated limit. So we designed our trailer for 18,000 pounds at an 18,000 pounds at an 8-degree slope. And from there, we determined that we needed a normal force of about 4,500 pounds to be able to generate a drive force of about 2,700 pounds. And it doesn't, and those forces just have to be applied wherever we have the drive system applied to.
So for our first preliminary design, before we met with Ditch Witch, we came up with a trailer tug. And this was going to be used at the front of the trailer to just pull it around. And after meeting with Ditch Witch, we realized that they were wanting more of something that's integrated into the trailer. And so a couple reasons that we weren't going to use this tug is that if going up a hill, with the tank in the back of the trailer, the weight distribution would create a lot less traction for our tug at the front. And as well as you would have to place it under the trailer and remove it back into a vehicle when you're not using it. Our second preliminary design is what we move forward with. This is actually a drop-down axle that would be mounted inside the trailer itself. This would go at the back to drive it. And for this idea, you can see here we tried to reenact these would be a telescoping ratchet. And so it would have substantially more torque, but the downfall to it is that you would have to either manually or electronically flip the direction, but that would also give you a safety brake for it not rolling backwards downhill or vice versa.
The complexity of the design is why we did not continue forward with the ratchet mechanism itself.
Yes.
And here we did some preliminary calculations to figure out how we needed to build that drop-down axle. And from that design, we had straight arm approximations. We made the members straight, we made the pistons straight to make sharp angles and triangles. And we used a lot of cosine to figure out the geometry. But the intention is to get the support arm as close to vertical as we could, so that way we can shift the weight that's being bared by the system to the arms, so the arms will bear the weight axially as opposed to the pistons having to take the weight. And here, we did some preliminary calculations using distortion energy theory, and we made the straight arm assumption, but we were able to conclude that we could use 3x4 by 3/8 rectangular tubing and still get a generous safety factor. But also, in our calculations, we made assumptions that these were straight members. And as represented by the red line on each of those members, the error was substantially higher on the straight member. So we ended up putting a bend in the arm to not only to create geometric clearance for the wheels and the motors and the pistons, but to also reduce the error that we had in our hand calculations versus what we actually foresaw the project bearing. And with trailers that are heavier than what we have, this is not their biggest trailer, but with bigger trailers, the same members could be used, the same arms could be used, but you could still beef up the bend in the arm by welding plates over those bolts.
So here was our final preliminary design that we went ahead and use the bent support arms, and we added a separate, or 2 cylinders to raise and lower it. Whenever this goes up under the trailer, you can see here that the 2 cylinders are mounting on the back of the main frame of the trailer, and the axle itself is going to be mounted between 2 of the support arms of the trailer, so there's no major modifications to the trailer to add this into an existing trailer. From the start of it, we could either do electric or hydraulic to drive it. We ended up using electric, and for the wheels, we had to use solid rubber wheels that are actually forklift tires. So the forklift tires we used, they're solid rubber and they're 10 inches in height and 6 1/4 wide. They're actually rated for 4,800 pounds apiece.
And the reason we decided to go forward with these wheels is because at that truck scale, we found at the front, approximately where we would have our front wheel would be about 3,300 pounds.
So for the steering of the trailer, we were originally going to use hydraulics to lift and lower it as well as steer it. So you can see here that we never made any major modifications to the trailer itself. So we just added a pin support for it to pivot up and down, and the cylinder would be on this main frame to raise and lower it.
And by this point, we had met with Ditch Witch, and we had concluded that we were going to separate the drive axle into 2 different motors, independently driven. And so, in finding the torque requirements that we needed to be able to generate those forces, the traction forces that we needed, we originally were under the impression that we had an operating pressure of about 1,200 psi. And so, with 1,200 psi and a motor displacement of 24 cubic inches per revolution, we found that the torque that we could generate was about 4,500 pounds. However, with this trailer that we have, we actually figured out that they have an operating pressure of about 2,400 pounds, which gives us twice the torque that we thought we originally had. But this original torque is what we needed to be able to keep that trailer on that 8-degree slope at its maximum weight of 18,000 pounds. And the reason we decided to keep the motors with the extra torque is because there's a lot of friction to overcome as far as steering is concerned. So the more torque we can generate, the better chances we have.
So for our final design for the drive axle, we actually split it and did 2 independent motors, and therefore we could place both of these at the back of the trailer and actually steer it from the back of the trailer. And so what we've done here is the hydraulic motor has got a dual sprocket and chain running straight to the shaft, and then we moved this cylinder to the center for the clearance of whenever it's pulled all the way up. The tire is actually touching the top of the trailer, so the cylinder is actually mounted over here. Here is a picture of it. It's actually mounted to the trailer, and as you can see, whenever we raised it up, our plan was to barely be off the ground with the tires. Well, we actually got it to where it does a push-up, and it is about 2 inches off the ground completely. For the front axle, because we can steer it from the back, we went ahead and just went with a crazy wheel for the front. We would like to have had a smaller surface area for the front tire, but because of the weight that the front tire must bear, we had to use the wider tire. Here is a picture of it in SolidWorks of ideally what it would look like whenever we had it manufactured. And as you can see, we made it to where the plate is perpendicular or parallel with the trailer itself.
And something that this picture does not show is that the location of that crazy wheel is directly underneath the motor of the trailer.
So here is the crazy wheel mounted into the trailer, and you can see that that is a 10-inch tire there, so there's only about 5 to 6 inches that it's actually below the main frame of the trailer. So going down the road, it's not going to hit anything. You hit a bump or run over something. And this is in SolidWorks of what ideally we thought it would look like when we got it manufactured, disengaged and engaged. And here we have a short video of the hydraulics raising and lowering. As you can see, the 3 cylinders are in parallel, so it raises and lowers in the path of least resistance. So they do not all go, they all go up at the same time. We would rather that the front one go all the way up, so we should have sequenced them to where the front would be parallel with the main frame, and the back where we could have We could have changed the pressure so that it didn't pick the trailer off the ground if we didn't want it to.
And as part of our design process, we decided to do stress analysis of the parts that we had. On this piece, we have the two longest members, the two longest C-channels. Those are representative of what's already on the trailer. And what we added were the mounts for the drop-down arms. And we also have the 4 pins where we connect the mounts to the arms. But with the steel that we used, we had a yield strength of 51 KSI, and we applied a generous load of 2,500 pounds per pin to find a max stress of 36 KSI. And with that maximum stress, that gives us a safety factor of 1.4. However, we also need to note that that was a very generous load that we applied at that point, and the weakest point was actually due to some geometry issues, mainly where those cuts are in the long C channel. It creates very high stress points. And also something that's important to note about this picture is that this is a very exaggerated representation of what the deflection of the member actually would be. And the next part we did the drop-down arms and the motor mount. And we used the same steel, so it's the same yield strength of 51 KSI. And we applied a load of 2,500 pounds across the bottom of the arm, represented by what the force of the ground would enact upon the arms. We also applied a torque of 4,500 pound-inches on the motor mount. We got a max stress of 21 KSI, which gives us a safety factor of 2.4. But the weakest point that we had there was where the motor mount meets the arms. So in practical application, it's a very easy thing to beef up if the need were required. And we also did stress analysis of the front half of our trailer. So here we applied a load of 5,000 pounds in the upward direction, represented by the ground. And we got a max stress of 10.7 KSI, giving us a safety factor of 4.7. Originally, the safety factor was about 0.6 because we were lacking, or between the plates and the mounts on the pin, we were lacking these two parts, causing this plate to warp up or to bend inward. So whenever we actually built the deal, we found that it was indeed warping. So we added these in here so that way we could get a generous safety factor. But also by having a very generous safety factor, we also build it to handle unforeseen loads due to, for example, turning. And we also did a stress analysis of the bottom half of that crazy wheel. So we applied the same 5,000 pounds force upward for the ground, but we also applied a side load of 2,000 pounds to simulate the force through the steering. And there we got a max stress of 34 KSI. That gave us a safety factor of 1.5. Originally, and whenever we built this, we found that the weakest point was in fact where this vertical rod meets that flat plate. And we found that plate was warping down on the trailer. So what we ended up doing is we added a second plate of the same 3/8 inch steel, which gave us the actual safety factor is substantially higher than what it was.
So some of the key components used for our design was an Eaton 2000 hydraulic motor, a 2-inch bore 8-inch stroke hydraulic cylinders, a remote and receiver, various valves, and the forklift press-on tires.
So this is the hydraulic diagram that we built for our circuit, or for our trailer. And what we ended up doing is we had two valves, one of which, the first one, number 4, was a 2-directional toggled valve that had the cylinders connected in parallel. And between the cylinders and the valve, we had PO checks that would essentially, the PO checks would open up and allow flow of fluid whenever we engage the valve. But whenever we disconnect, or whenever we return the valve to its neutral or closed state, those PO checks would lock the cylinders in whatever position we leave them in. And beyond that valve, we had another manifold that had two directional valves that were connected to the hydraulic motors. And we also had a valve between the motors and this valve to create a lock that would seize the motors whenever those directional valves were not open. And the way those operate were, if the line is pressurized, those lines open up and allow the motor to turn freely. But whenever the valve side of those lines is not pressurized, those locks close and they act as a brake, so to speak, for the motor.
So for the cylinders that we used, Ditch Witch provided us with 3 hydraulic cylinders that are the 2-inch bore and 8-inch stroke, and our max pressure for those was 3,000 psi. And so for the proportional valve that we used, the operating pressure for it was at 4,600 psi, and the hydraulic motors that we used were 24 cubic inch displacement with the operating pressure of 2,250 psi.
And this is the circuit diagram we ended up coming up with for our controller of the hydraulic system. On the right side, we have the tethered input remote, and that remote consists of 2 potentiometers that acted as they gave the measurements required. So each potentiometer would control 2 solenoids, and there's 2 solenoids per directional valve. So one potentiometer would control one directional valve, and the other would control the other directional valve.
So this is the controller that we used. It is an Axiomatic quad controller. This controller allows us to control 4 outputs with only 2 inputs. And the black side, as Connor said, is our tethered side where our remote went into, and the gray side went out to our proportional valve. This is the service program that came with the tool. If you can see the yellow line on the top graph right there, 2.5 volts is neutral on our left motor and our left potentiometer on our remote. And when you push it forward, it jumps up to 5 volts, which is full forward. And when it falls down to 0 volts, it's full reverse. And the same thing on the bottom one, the purple line represents the right potentiometer and right hydraulic motor.
And this is the remote we ended up coming up with. Originally in our design, we had just regular knob potentiometers. And aside from one of those knob potentiometers being broken, we decided to go with joysticks instead, because the neutral state of those valves is whenever that input signal is at 2.5 volts. And so whenever, this is also a big safety issue, because whenever, with a toggle switch, or with a knob, if whatever value you leave that knob at is going to be the value that is returned to the motor. So by having the joysticks, what we're doing is we're creating a safety net where if you let go of the remote, those toggles are going to return to the neutral position and shut those valves and break the trailer. So
this is our failure mode analysis page. What the team came up with was our highest risk priority number would be traction loss and slipping of the trailer. In worst case scenario, if the trailer is sliding, it could cause harm to nearby people or nearby property. Next was a failure of any of the support arms. This would cause the trailer to collapse, and anyone underneath the trailer or around the trailer could be harmed, or any property that the trailer is over could also be damaged.
So for our testing purposes, we wanted to look at our velocity. We did this by running 2 trials to account for variability. We measured out a distance of 20 feet and used a stopwatch for our time. We were able to find that our average velocity was 1.1 mile per hour, which as specified by Ditch Witch fell between the range of 1 to 1.25. We also wanted to test how effective our trailer was able to stop. And as Connor was mentioning, as soon as you release the throttle from forward to neutral, the trailer would actually stop almost instantaneously. But as mentioned, we only tested this on a flat surface. We haven't tested it on an incline or a decline. And also we wanted to just see how much traction we were able to get on grass after a few days after it had rained. And as expected, we weren't able to get very much traction.
yeah, the reason being is because the trailer, as you would normally operate it, it has 5 points of contact. With the 2 tandem axles, you have the two tires on each side, as well as the tongue or the jacker where it's hitched. However, with our particular design, because it lifted the trailer up off the ground, we reduced the number of contact points down to 3, which created a very high pressure in those points, resulting in the wheels sinking into the ground. And so from testing, we were able to draw a few conclusions about our design process. And one thing we found is that the location of the motor, it resulted in a very disproportionate amount of weight over the front crazy wheel, and also with us lifting the back end of the trailer off the ground, we shifted more of the center of gravity of the trailer forward as well. And what this ended up doing is that front crazy wheel, the rubber on the tire compressed substantially, and it resulted in a very large footprint that gave us a lot of resistance whenever we tried to turn. So the turning resistance was in many cases higher than the turning force we could generate by the drive motors. That's not to say that the trailer can't turn, but it's a very finicky process, and it takes a lot of moving around to get it to actually turn where you need it to. And some of the solutions we were able to come up with to solve this problem, we found that we figured we had enough displacement on the hydraulic motors that we had, but the problem was we were having a difficult time generating the right amount of torque. So one solution to this would be to increase the pressure that those motors have. And so if we replace the hydraulic pump on the trailer with more pressure, we could get higher turning torque. And some of the other solutions we had included adding an additional crazy wheel in the front that would be able to split the weight. And with the weight reduced per tire on the front, we could have a smaller tire, so to speak, and reduce the amount of turning friction that those tires generate. And we also, along the lines of that idea, we could also add hydraulic motors to those front crazy wheels to help them pull themselves along as well. And something else we could have done would be to add a servo motor to assist in the steering of that front crazy wheel. And something else that we attempted to do was we attempted to find room to fit in a gear reducer, a gearbox that would be able to generate more torque given the hydraulic pump that's already on there. But for simplicity and the design's sake, we decided to keep everything in line. And
So I just wanted to say special thanks to Richard and everybody at Charles Machine Works for donating all the materials along with helping us fabricate all our parts. And Travis Peterson, who donated the proportional valve to us, as well as Wayne and everybody in the BAE lab that helped with our putting everything together. And then also Dr. Weckler, Dr. Long, and Dr. Wang.
do we have any questions?
Questions for this team? What was your ground clearance when everything was folded up? In other words, what was the minimum or what was the riskiest area?
The minimum on the rear was the kind of limiting factor of it. We were just about 1.5 to 2 inches below the rear axles, the tandem axles. So for them to touch the trailer, the back of the trailer would have to be touching the ground as well. And it will, if you back up to a curve with it, the drive tires are actually about 6 inches behind the rear axle tires. And so it would, if it's a tall curve, it would hit them first, but a normal size curve, it will kind of be over the top of them and it won't hit.
If you were going downhill, is there any concern about trailer running away? Did you have any brake?
Yes, that would also be something that we would actually design for as well. Is on the remote, something that we would like to do is put in a logic function that if the valves are open, then have a brake or something that connects to the trailer's brakes, or turn off that brake. But whenever the valves are closed, that brake will engage. That would be something I don't look at, but for our purposes, the braking function of the hydraulic motors and the PO check valves that we had was sufficient. Yeah.
Earlier we were comparing the straight beam for the supports for the wheels and the end piece. You said you had given a generous safety factor. What was that generous safety factor?
Most of my stuff I tried to design for around a safety factor between 2.5 to 3. And the reason is because with something that weighs 18,000 pounds, you don't want anything breaking and going wrong and potentially injuring somebody. So we generally try to aim for around 2.5 to 3.
What kind of configuration changes would you have to make to run this on non-asphalt, non-concrete surfaces?
We would, or the main thing we would have to do is, a major problem we have, I guess, is the torque that we need to turn it. So that's one issue in and of itself. But whenever we had the trailer sinking into the ground and whatnot, that was because we had so much weight on 3 relatively small areas. So ideally, what we could do is also, if we could control how far those rear arms extend downward, we could keep the tandem tires that are already on the trailer, we could keep those in contact as well and have 4 additional contact points to help spread out the weight and keep us from sinking in the ground. But aside from that, we also, a design change we're also contemplating would be to change the frame, I guess, of and this is just theoretical, I guess, change the way the deck is built, so that way we could accommodate larger tires and increase the surface area and possibly get better traction out of those, because these are also ball tires just because of the weight that they have. Yeah.
Did you give any consideration to how this would behave on a side slope?
So the way we did that is, or like we were saying, the intention was originally to have the tandem axles in contact with the ground as well. So in an ideal situation, we would be able to.
We would make the rear to where you could apply just enough pressure to just barely, to take weight off of the trailer so we had enough traction to drive it.
And
So you would have the actual tandem axle tires to be able to help support yourself on a trailer, or on a slope.
Yeah.
Sideways.
And so if the trailer itself, I guess, without these drop-down axles engaged, can keep from toppling over, I guess that would be what we would expect on here as well. However, with the way we have it set up now, there's no feasible way we could steer it on a slope like that. But that's because the steering mechanism will need to be redesigned if this process goes forward. So.
On your speeds for the forward and backward, is it basically a fully open and or is it a modulating valve? So is it constant speed or?
So they're proportional valves.
Okay.
So it's not, it's not all or nothing. It will open partially if you yeah.
And then it looked like on your speed tests that your average speed was higher than your 2 trials. Was that just a rounding error?
Go back to the, I converted. Yeah, that was a feet per second. Minutes mile per hour, I just averaged those 2.
So is that just a rounding error? I
Yes.
guess?
Yeah.
Okay.
Any other questions for this group? Well, they will be driving this around the parking lot over at the Biosystems Lab later this afternoon. So let's give this group a round of applause.